everyone, welcome back to my channel. Today we're diving into the fascinating world of bioinformatics file formats. Now, you might be wondering, why should I care about file formats in biology? Well, my friend, let me tell you, this is one of the most crucial aspects of modern research and data analysis in the biological sciences. So, buckle up and get ready to have your mind blown. In this playlist, we'll be delving into conversations surrounding the FASTA and FASTQ file formats. If you haven't already subscribed to my channel, I encourage you to do so for the most up-to-date videos and solutions related to bioinformatics. I'm delighted to have you all here. In this video, I'll be covering two frequently utilized bioinformatics file formats, FASTA and FASTQ. FASTA file examining the FASTA file. This is essentially its appearance. It's essentially a text file that can be opened in any text editor such as Notepad or Microsoft Word. This file is utilized for storing nucleic acid or amino acid sequence. In the example provided, we have an amino acid sequence where each amino acid is represented by a one-letter code. Each FASTA file is divided into two parts, a header and the sequence. The header always begins with a greater than symbol and includes relevant information about the sequence. A FASTA file can either contain a single sequence or multiple sequences. If it has multiple sequences, each subsequent sequence will begin with another greater than symbol. The line containing information is followed by the sequence. The file extensions for FASTA files include the FASTA UFA, and it can also be .fna, indicating the file contains nucleic acid sequences, or UFAA, suggesting it contains amino acid sequences. This format is commonly used for reference genomes and Sanger sequencing, as well as some older NGS sequences report the sequence in this manner. FASTQ file in the FASTQ format. Files not only store nucleotide sequences, but also include information about the corresponding quality for each nucleotide. FASTQ files commence with the TT symbol, and the first line serves as the description line, akin to the description line found in the FASTA file. This description line provides details about the instrument type, run aid, flow cell ID, and other relevant information. The second line contains the actual nucleotide sequence, while the third line starts with the character, followed by the same sequence ID or description line. The last line corresponds to the quality scores, where each character or letter represents a quality score, also known as a Phred score. Further details about Phred scores will be discussed in the next slide. Sequencers generate these files, and they find utility as input for aligners, quality control tools, and assemblers. The file extensions for FASTQ files are FASTQ or FU. Phred scores essentially convey the machine's confidence in accurately identifying each base. A higher Phred score indicates lower probability of an incorrect base call. The table below illustrates that as quality scores increase, the probability of error decreases. Each quality score corresponds to a character, and this character signifies the quality value for a specific nucleotide. To provide a more tangible example, suppose a machine reads an adenine nucleotide and assigns it a quality score of Q20 in Phred scale. This implies a 99% certainty in correctly identifying the base. While 99% confidence is high, it still means there's a 1 in 100 chance of error. In the context of a 30x genome with around 90 billion base calls, a machine with a WAND error rate would make incorrect calls in 900 million bases. This underscores the importance of low error probabilities and high Phred scores in base calling. In summary, this discussion covers the principles of the FASTA and FASTQ formats, emphasizing the significance of quality scores, particularly in ensuring accurate base calls. In conclusion, understanding the FASTA and FASTQ file formats is essential in the field of bioinformatics. The FASTA format, characterized by its simplicity and use of headers to store sequence information, is commonly employed for storing nucleic acid or amino acid sequences. On the other hand, the FASTQ format goes a step further by not only storing sequences, but also incorporating quality scores for each nucleotide. This additional layer of information is crucial in assessing the reliability of base calls. Both formats play pivotal roles in genomics, with FASTA often used for reference genomes, and FASTQ files generated by sequencers serving as valuable inputs for aligners, quality control tools, and assemblers. The Phred scores associated with FASTQ files provide a standardized measure of the confidence in base calls, crucial for accurate analysis in the vast landscape of DNA sequencing. In summary, mastering the intricacies of FASTA and FASTQ file formats equips researchers and practitioners with the foundational knowledge needed to navigate and analyze biological data effectively. As technology advances, these formats continue to be integral components in the broader landscape of genomic research and bioinformatics. Get ready to explore the hidden world of bioinformatics file formats and uncover their vital role in modern biology. In the next video, we will discuss about VCF file format and gVCF file format. I trust you found this video to be informative. If it provided value, kindly consider subscribing, liking the video, sharing it, and leaving your comments in the comment section. Until our next encounter, take care and see you soon.